So I gave a riddle to my Calculus 1 class, and I've given them like a week and no one has solved the riddle. So I'm going to give you guys the opportunity to solve this riddle. And if you've heard it before, don't ruin it for anybody, but because it's just such a wonderful riddle. So here it is, and you can tell me if you've ever heard it before. So the story is that like somebody's very, very mean and you were poisoned, and they're going to give you the opportunity to like cure yourself. And so what happens is they set 12 pills in front of you, okay? And these 12 pills look, smell, taste, everything is exactly the same. The only difference is the one pill that will cure you is of a different weight than the rest of them. So 11 of them weigh the same. The one that you're interested in taking weighs differently. That's all you know. Okay, so you've got 12 pills. Okay, and all you know is one of them weighs different. And you've got to figure out which one it is. And this is what you're given. You're given a balance scales. And you're going to be allowed to use the balance scale 3 times. And that's it. Okay, so at the end of using the balance scale 3 times, you have to be able to tell which is the antidote pill. And all you know is one of the pills weighs different than the other 11. And the other 11 weigh exactly the same. Okay, and I always give a hint because it never fails. Somebody raises their hand and says, I know. And it's like, no, you don't. Okay, this is kind of a tricky problem. Has anybody heard this one before? Oh, you have? It's a good one, isn't it? Oh, I told you it? Oh, good for me. It was a good one to tell. So here's a hint, okay? It's not a very big hint, but here's a bad first idea. Put 6 on one side and 6 on the other side. Okay, that's not a good idea. Why? So it goes like this. So what did you just learn? Yeah, that it's either a heavy pill over here or it's a light pill over here. So what you just learned is it's one of those 12 pills. That's no good. Agreed? So there's kind of 2 things you have to determine. You kind of need to determine, is it heavy or light? You also need to determine, well, which one isn't. Does that make sense? Okay, and so you get to use the balance scales 3 times, and at the end of 3 times, there is a way to know exactly which one it is, no matter what happens on the scales. Does that make sense? Okay, this is a very fun problem. So, and you feel very good about yourself when you get the answer, so it's worth it. So I would suggest trying to figure this one out. If you think you figured it out, you can come by my office sometime or talk to me before or after class, and I will be happy to tell you if you got it right, okay? And you don't spoil it for anybody. It's too good. It's too good. Okay. So let's get started. Just a quick reminder, on Thursday, we will do presentations. And it would be really great if maybe you could email me your presentation, and then I could just kind of have them all loaded up and ready to go, so there's not a lot of lag time in between people like setting up and everything. So if you just email me your presentation, I'm assuming everybody's using either Google Slides or PowerPoint. As long as there's no weird stuff going on. PowerPoint, Google Slides, I'll load everything up, and then we'll just get started when we get here, okay? And then we won't have to switch in between computers between every group. So email me your presentation basically by like 8:30 on Thursday morning, okay? And then I'll have it ready to go for you. Let's see, anything else to say? I don't think so. So today we're going to just keep talking about our rules of inference. So let's see, let's start with the definition. So we say that P is provable from a set of premises if there is a proof of P from the set of premises. Okay, pretty straightforward definition, but still important because you can have a set of premises from which, like, some conclusion is not provable. Now, just because, and also because something's provable doesn't mean you have a proof, right? So there's a difference between, like, actually writing a proof and saying that something is provable. Okay, so let's talk about another rule of inference. What was the first rule of inference? Yeah, modus ponens, right? And there's actually a second rule of inference that's mentioned in the book that I don't cover, and that's adjoining premises. And basically what adjoining premises says is the following. If I've already done this work in a previous proof, then I don't need to do it again. Okay, and so practically for us, that's not going to make a huge difference, but you will use it because you'll kind of say, hey, in the proof I just did, I proved this little piece. And so I should be able to use it again in this proof. And it's like, yeah, you can. And that's one thing that's really nice in mathematics is that we don't do the work 14 times if we can do it once. So once you've proved something, you can just state, remember we proved that, and then use it. Okay, and you don't have to keep using it, proving it over and over again. But I'm not going to write anything formal on adjoining premises. This one I want to talk about is direct proof of implication. Also, I'll just abbreviate this DPI because I don't want to write direct proof of implication. Okay, so and what direct proof of an implication is to prove that P implies Q from premises capital R, we may add P to the premises and prove Q. Okay, and this is based on a tautology. Okay, and so let me write the tautology that this rule of inference is based on, and that is that R implies P implies Q is true if and only if, or in other words, is logically equivalent to in some sense. R and P imply Q. That's a tautology. Now, how is this helpful to us? Basically, what this says is that if you're trying to show that R, you can think of R as like all the things we know are true, right? R is the set of all known truths. And you want to show that P implies Q from R, then it's the same as saying that R is true and P is true, and then just showing the Q. So what I can do is I can just say, let's just say that P is true. Is P true? I don't know. I'm not saying that P is true, but I get to kind of play as if it is true. And then if I can show that that means that Q is true, that means that I've proven that P implies Q. Remember, if you prove that P implies Q is true, that doesn't mean that P is true or that Q is true. It means the implication is true. And that's what I'm trying to show, is that P implies Q. But one of the ways you can do that, what can you tell me if P is false? Well, Q isn't necessarily always true, but P implies Q is always true, right? So if P is false, then I'm kind of done, right? It's like, yeah, sure, P implies Q. Agreed? But if P is true, then I need to show that Q is also true to show that the implication is true. So when I assume that P is true, it's kind of like, because if not, we're done. Does that make sense? So if P is false, then the implication is true and we're done. If P is true, well, then Q better be true as well. So that's what we call a direct proof of an implication. Sometimes I'll just call it a direct proof. Okay, let's do an example of this. So, premises. We have two. We have P, and we have that Q implies that P implies not R. And I'd like to prove that Q implies not R. Now, note there's something different here than what we've come up against so far, and that is that the thing that we're trying to prove isn't just like prove S. I'm not trying to prove a statement. I'm trying to prove an implication. Right? Now, proving an implication, and this is a big deal, there's a couple different ways to deal with it, and we're going to learn all of them. But the first one is what we call a direct proof. And the direct proof is I'm trying to prove if something, then something. Then what I'm going to do is I'm going to assume that the hypothesis is actually true. And then I'm going to prove that the conclusion is true. And if you do that, then you prove that the implication is always true. Because if this one's true, then this one's true. And if this one's false, then the implication is true. Everybody with me? Okay. So a direct proof says just add this to the premises, the hypothesis, and then get to work trying to prove the conclusion. The power of the direct proof is you know how it starts and you know how it ends. It starts with the line, assume that Q is true. It ends with the line, so not R is true. And if you do that, then you're done. Make sense? Okay, let's write a proof. So I'm going to start by I assume Q. Now, again, Q isn't part of the premises, but it is the hypothesis of the implication I'm trying to prove. So my justification for assuming Q is I'm doing a direct proof. Does that make sense? So I start by just saying, hypothesis is true, or let's assume it is. Okay, so Q is true, now what? What do you think should be my second line?
Use the second premise.
Yeah, let's use the second premise that Q implies something, right? So I know, and we have that Q implies that P implies that not R. And that's just a premise. Now what can I say? Yes, sir?
Since we're assuming that Q is true and that the premise is true, then P implies not R is true.
Yep. So P implies not R. And why is that? Modus ponens, right? I have truth, and truth implies some other truth. So this one must be true by MP. What now?
When P is true.
Yeah, P is true. Also, P is true because it's a premise. And now I have P is true, and P implies not R. So I can say, therefore, not R by modus ponens. And so I've proven the conclusion. Agreed? Now, when you're doing a direct proof, there's one more line. And that is that, okay, I started with Q, I proved not R, so now I can say, therefore, Q implies not R is true. And the reason is direct proof of an implication. So I started with the hypothesis, I proved the conclusion, therefore the implication is true. Because if the hypothesis is true, the conclusion is true. And if the hypothesis is false, the implication is true. Does that make sense? So it has to be true. Okay, very good. Any questions on this one? So this is like our bread and butter strategy for proofs. Okay, it's like this is what we typically try first, is to do a direct proof. If somebody's saying, prove that if blank, then blank, then what you say is, okay, assume the hypothesis, do some stuff, therefore the conclusion. That's like the bread and butter proof, and that's what you've kind of done in geometry, honestly. Like geometry proofs are basically direct proofs. You say this, so this, so this, so this, so this, so this, hooray, right? And so that's kind of maybe what you might try first if you come up against a proof, but it's not the only way to go. So we'll learn some other stuff. So next rule of inference. This one is substitution. Substitution is if S is true if and only if R, then we may substitute R for S as equivalent statements. Okay, let's give an example of this. Maybe. here's an example. Let's say we have some premises. We have Q or P. If and only if. Not Q implies P. We have not Q. We have R implies that Q or P. We have R. Maybe I'll just put R. Okay, I want to prove P. Okay. Notice, first of all, that I'm not doing a direct proof, because a direct proof always is proving an implication. This, I'm just proving some statement P. So now I just need to kind of figure out, okay, what should I use of my premises to start to prove P? So proof. Where do you think I should start?
Because we have not Q, I'm going to speak really loud.
Yeah, you're fine.
We have not Q as one of our truths, would that imply that the rest of the Q's in our premises are false?
It would. So if we have not Q, that means that Q is false. That's true. And maybe that is helpful in some way in here. Yeah, but it's certainly true. Yeah, Q is false. That's right. So where do we want to begin?
R.
I like that. Yeah, R. Let's start with R. So I'll just say R. And again, we're getting lazy now. And we're not saying, assume that R is true. It's like R means R is true. And what's our justification for that? It's premise. Okay, now what? Yeah, we've got that R implies the Q or P. And that's also just a premise.
Are you able to start with just R implies Q or P because it's a premise?
Yeah, could I start with
Like,
it?
do I have to say R? Because,
You do.
okay.
So, because if you don't know, so of course modus ponens, right, is that you have an implication and you know the hypothesis is true. If I just say that this is true, like let's say we don't know that that's true, then I don't know if either of those are true. In fact, this could be true and both could be false.
Yeah.
Agreed?
Yeah.
So, but as soon as I say R is true and you know that this is true, then you're like, oh, if this one's true, that one has to be true. Yeah, so you do need to say R. Okay, so now what? Yeah, Q or P by modus ponens. Now what? Yeah, now we can use our new trick, right? And that is that we could just make a substitution because I know something that is logically equivalent. I know that this statement is logically equivalent to this statement. So I'm just going to make the jump and I'm going to say, so that means that not Q implies P by substitution. Now, somebody might ask, do you need to write that line in before you make the substitution? It's up to you. If somebody were like asking you, how did you get from here to here? You kind of say, well, I just substituted. And then it would, of course, beg the question, what did you substitute? And if it's sitting right here in the premise, it's okay with me. But some people like to write a line right in here that we know that this, if and only if this, and so this. Either is okay. Yes, sir.
Are you able to, from the Q or P part, when it says not zero, are you able to say therefore Q?
Like, can the next line be P?
I'm referring to the line before that.
Oh, this one?
Yeah.
Oh, yeah, that's an interesting question. So you're saying that there's something else we should know, right? And that is that if Q or P and not Q, then that implies P. That is so true. But in this case, because I want to demonstrate substitution, I'm not going to do it right now. But you're absolutely right. In a lot of these kind of like symbolic proofs, those kind of things come up where it's like, oh yeah, that actually, you could do it this other way too. So I'm just kind of trying to do some demonstrations of this stuff, but that is absolutely right. Yeah. So, so what should be the next line just following this line of thought? Not Q, yeah. And that's premise. And now I can say because not Q and not Q implies P, then therefore P, which is actually what I wanted to show. And the reasoning is, yeah, in P, and we're done, right? And so I should probably end my proof. I think I forgot to do that. Any questions? Okay, so substitution is pretty straightforward. If you have two logically equivalent statements, then you can just jump to the other one, if that's helpful. Sometimes it will be, sometimes it won't. Okay, another rule of inference. This is called a contradiction. Also called an indirect proof. And here is the tautology that a contradiction is based on, or an indirect proof is based on. And that is that P and not Q imply something false is true if and only if P implies Q. And that's a tautology. Okay, this is a very powerful tautology because sometimes you want to do a direct proof of an implication. And so you start out and you say, assume P is true. And then you do some stuff and you're like, man, no matter what I do, I just can't prove Q. And so this is when you typically say, I know, let's try something else. Let's try to assume that P is true and that Q is false. And then if I can prove that that leads to something crazy, then I'm done. Now, direct proofs are super powerful. And the reason why, indirect proofs are super powerful. And the reason why indirect proofs are super powerful is you get more to start with. You know, the more premises you have, the better, right? The more truth you get to work with, the better. And you get more truth to work with. The bad news is in a direct proof, you know what the end line is. It's the conclusion, right? You start at the top with the hypothesis, you do some stuff, you end with conclusion. In an indirect proof, you start with some stuff and you do some work, and where does it end? When you get something that's wrong, that's harder to know where you're going. And so indirect proofs in that way, that's its downside, but the upside is you get more to work with. So it's kind of a trade-off. But some people find that once they learn about indirect proofs, they really never want to do a direct proof anymore because you just get so much more to work with. So let's try one. So let's do an example. Here are premises. We have not P or Q implies not P and not Q. And yes, I do, in some sense, this is sort of kind of a De Morgan's law, but we'll ignore it for now. We have not P implies R. We have not Q implies not R. We have not P and not Q implies not P. And we have that not P and not Q implies not Q. Okay, so you can already see that this is going to be a little bit different. There are a lot of premises, and there are no like easy ones, if that makes sense. There's no like P. That's nice when you're trying to write a proof. So this is what I want to prove. Prove that P or Q okay, so first of all, this isn't really, you could say this is an implication, or you could say it's not. What I really would like to say is all of this stuff implies this. So it is an implication of a sort if you consider all of the premises to be like if all this stuff, then this guy, right? So if you can kind of think of this as a conclusion of sorts. So first of all, if you wanted to do this proof directly, where would you even begin? And I think you maybe, after looking at it for a few minutes, would say, this is a problem. I don't really know what to start with. Nothing is jumping out at me as like helpful, right? Yeah.
Okay. Well, we have a recurring theme of not P and not Q in our premises, and by De Morgan's law, not P and Q in our first premise.
Yeah.
Is an equivalent statement. So I think our goal would be to prove that not P or not Q is false, therefore not P and not Q are always true.
Yeah, so I hear what you're saying. Again, we've got to kind of be a little bit careful. Like, De Morgan's law is definitely true. But in our world of this proof, we don't know anything about it. All we know is this stuff. This is the truth of the world is contained right here, right? We know nothing else. So even though you're totally right, De Morgan's law is true, and we know some other things, this is what we know right now. And I think it's hard to start, right? I don't really see any nice way to do this. But if I think of an indirect proof or a contradiction proof, there is a way to start. I say that this is false, and then show that that is absurd. Okay, so this is what we're going to do. So proof. I'm going to start, and I do something kind of different. Not everybody does this. This is kind of like a notation that I use personally. And I could just say, assume this is false. But I'm not going to do that. I'm going to suppose it's false, and I'm going to use a little symbol. And this is like a little S with a P on the bottom, and that's my symbol for suppose. And I only use this symbol if I'm about to say something that I think is false. Like, it helps me to remember that I made a statement that I actually think isn't true. Is that helpful? So I will only use this symbol typically to do a contradiction proof. It helps to remind me, oh, I'm doing a contradiction proof. And it helps to remind the reader, in some sense, that you made a statement you don't even believe. Okay, so what I'm going to do is I say, suppose it's not the case that P or Q. And my justification for this is an indirect proof. So I'm starting an indirect proof. Okay, once I've made that statement, is that helpful to all the other premises that I have sitting around here? Yeah, actually, then you're like, oh, the way forward becomes illuminated. And that's actually what happens in a lot of like mathematical proofs too, is that once you assume the negation of the conclusion, you're kind of like, oh, I know what to do. But we don't exactly know what the end is either. So let's start going. But I think we do know what to do next. And what is that? The first premise, right, will be helpful. So we can say, we know that not P or Q implies that not P and not Q, because it's a premise. And so we can conclude from the first two statements that what? So, what should I say? Yeah, not P and not Q by correspondence. Everybody with me? Yeah.
So if we know that not P or Q is false, or if we're assuming that that's false, when not P and not Q, is there a possibility that not be false?
Okay, so say that again. Am I assuming what is false?
So, like, the first thing we assume is false, and then you have not.
Okay, so this thing, I think that this is false,
Yeah.
but I'm assuming that it's true. So what I just said is, this is true. Now, it's not true.
Oh, okay, yeah.
Does that make sense? But I'm working with it as if it is true. So that, maybe I didn't say that well, but thank you for the clarification. What I'm saying here is, this is not this. That's a true statement. Now, I don't believe it, but I'm going to work with it. Does that make sense? I don't believe this statement, but this is acting truth right now. Are you with me? And so right now, this is a true statement, and this is a true statement. So this must be a true statement. Okay? Now what? Is that helpful in any way?
Yeah. P and not Q implies not Q.
Yeah, we've got that not P and not Q implies not P, and we have that not P and not Q implies not Q. So we can use either of those. Let's start with, we know that not P and not Q implies not P, because it's a premise. And so I could conclude from that what? So that means not P. Okay, very good. By correspondence. I could do the same thing for the statement. We know that not P and not Q implies not Q. That's a premise. And so I could say the same thing. So that means not Q by exponents. Okay, so I know that not P is true. I also know that not Q is true. What do you want to do now? Yeah, not P implies R. That might be helpful. We know that not P implies R. That's a premise. And so using this guy, not P, and not P implies R, I can combine those to get so R. That's by P is over here. And now we can use, which one did I already use? I used this one. Now I could use this one. And I could say, we know that not Q implies not R. That's a premise. And so we know that not R by exponent. And so what we have here is we know that R is true, and we know that not R is true. So I can say so R and not R. But this is what we call a contradiction, because this is impossible to be true, right? We know that this is false. This is just by basically a definition of and. And so typically what I do here is I write in my little contradiction symbol. So I came to a place where that's ridiculous. I can't have R and not R. As soon as I get to that place that it's implied a contradiction of some sort, then I say, so what I said at the beginning, what I supposed was true, is actually false. So this thing cannot be true. So that means that I could say, therefore, the negation of that is true. So P or Q. And that's by an indirect proof. And that's what I wanted to show. So we're done. Okay, so you can either prove that P implies Q by assuming P and proving Q, or you can prove that P implies Q by assuming P, assuming not Q, and proving contradiction. Those are two different strategies that are equally good. Everybody good with that? Okay, these are more tricky when you get started, because in like geometry class, you did direct proofs, typically. If you had a very good geometry teacher, maybe you did an indirect proof, I don't know, but typically not. So when you get these in the book and you start doing homework over indirect proofs, I think that this is harder because you don't know where it ends. So you have to just kind of keep working and try to find something that is wrong. Okay, let me write a few more useful tautologies. So additional useful tautologies. this is actually even another proof technique. This first one is that P implies Q is true if and only if not Q implies not P. And what is it we called this again? Like this statement and this statement. What is this statement called? Yeah, that's the contrapositive of this statement. Now, this brings us to another way that we could prove something. And that is, instead of starting with P and proving Q, you could start with not Q and prove not P. That's called the contrapositive proof. Sometimes sometimes people say, well, isn't that just kind of the same as the indirect proof? And it's like, well, it's all about where you end. Because in both cases, you get to assume not Q. But in one case, you assume, in the indirect proof, you also say that P is true. In the contrapositive, you do not say P is true, and you prove that not P is true. So that's called a contrapositive proof. Does that make sense? So now we actually have three different ways. We'll practice all of these plenty of times, don't worry. But we have three ways to prove things: direct proof, indirect proof, contrapositive proof. And they're all the same in terms of what they do. They all prove an implication, P implies Q. Okay, another one that is helpful to us is not Q or S or Q.
Wait, did you say or?
Oh, sorry. Believe what I write, not what I say, I guess. Yeah, and. Not Q and S or Q implies S. And this is actually what you mentioned just a little bit earlier, right? That we have this, I think, exact situation, that we had an or statement and we know one of them's false. So if you know that this is true and this one is false, then the other must be true. And so this is something that we use a lot.
When we use a tautology like that, what do we put as our justification?
Yeah, I think it's good enough to just put logic. Okay. I'm willing to buy a story that if you say one of these two things is true, it's not this one, then it's this one. I'm fine with that. You can just put logic. If you ever come up with something like that where it's kind of like, this is obvious, but I'm not exactly sure, this isn't modus ponens exactly, but it's obvious, you can just put logic. Okay, 3, not R is R, which is obvious, but helpful. And P implies P or R. This one is another one of those ones that makes people angry sometimes, but it's absolutely true. And that is that if I tell you that something is true, then that thing or another thing is also true, right? So if I say 1 + 1 is 2, and you're all like, sure. And I say 1 + 1 is 2, or the moon is made of cheese, you should say, sure. Right? Even though one of those is false, it's okay because I can or anything I want to on, and it's still true. So this is just saying you can, once you have established one thing is true, that or something else also is true. All right, a couple definitions we need to know. So definition. If we can prove P from a set of premises, then say that P logically follows or simply follows from the set of premises. Sometimes you just have to learn language to sound very, very pretentious while you're explaining your proof. And you can say things like, and it logically follows that, da, 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 or it follows that, anyway. So basically all you're saying is that if you can prove something from a set of premises, then we say that it logically follows that, let's say. Okay. Another definition. An argument is a sequence of steps proposed as a proof. If it is a proof, we call it a valid argument. If not, it's called an invalid argument. Okay, so if you hand in a proof to me, we will all agree that this is an argument. Okay, so you're making an argument about why this proves something. And then if I say that you got it right, it was a valid argument, right? And if you say something that actually logically didn't make any sense, then we would call that an invalid argument. So an argument in and of itself has nothing to do with proving truth. It's you tried to prove truth. A valid argument actually did it. Okay, so pretty straightforward. But these are words mathematicians use. It's like somebody says, I think that if this, then this, and somebody will say, well, show me your argument. And it's kind of like, I'll be the judge of that. You know what I mean? So what's your argument? Okay, any questions? That's the end of this section. So it's a good time if there are any questions about anything. Yes, sir.
I don't know if this really kind of a question for this, but can you go over any of the homework today or no?
Oh, from the last set.
Yeah, let's have one question.
Okay, I don't have my book with me right now, but you could just read it to me. It's okay, unless it's really long to read.
There was numbers. I'm actually right.
Okay.
For the following tautology, in parentheses, P and not Q implies a contradiction is logically equivalent to P implies Q. I think that was yeah.
Oh, that's not even a contradiction.
Is this the one?
Oh, I said O was another.
Yeah, no. Isn't there?
They have a
Oh,
different
yeah,
symbol.
they use a different symbol for contradiction.
Oh, they used a different symbol. That's mean spirited. Yeah, you're good now though. So in the truth table that you make for each of these statements, this one just is always false. Yeah, I think I remember a version of the book that they printed where they used a bad symbol for contradiction. That is not typical at all. That everybody uses this for contradiction.
Okay, so that whole last section would be all false?
No. So basically what you could do is you could say, like, there's P, there's Q, and there's contradiction.
I see.
And it's like P is true, true, false, false. Q is true, false, true, false. And contradiction is false, 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 false. He never gets to be true. Does that make sense?
Yeah.
And now you can do the P implies Q, which of course is true, false, true, true. And then you could do the P and not Q implies contradiction. And of course you could do this and you'd get true, false, true, true. And at least that's what you should do. Does that make sense? So if you do this piece of it to show that their columns are the same, you should get the same.
Okay.
Yeah. Yeah.
I had a question on 20.
Okay. What was number 20?
Reformulate each of the following so that the resulting logically equivalent statement has only not and or as connectors.
Okay.
And it's the converse of P implies Q or Q or R.
Okay. I might need to look at, does somebody have a book that I can just look at? That might be helpful. Okay, so 20, reformulate the following so that the resulting logically equivalent statement has only not and ors as connectors. Okay, so we want P implies Q or R. Yeah, okay. Okay, so first thing is that we have like what's called the or form of an implication, right? And what is the or form of an implication? So if you have, forget this one for just a second and say, what if you have P implies Q? What's another way of saying P implies Q with ors? Yeah, not Q or P. These two are logically equivalent. So how could we use that to work on this? So we have P implies stuff. That's the same as not that stuff or P, right? So we could say it's not the case.
Yeah, you are working with the converse of it now, right?
Oh, did they say the converse of
Yeah,
this?
it said do the converse.
All right. That's fine. So what is the converse of this?
Q or R implies P.
That is, yeah, okay, yes. So Q or R implies P. So they want you to work with this one.
Yes.
Okay, very good. That's good. So forget this guy. We want to do the same thing with this, right? So we have something implies something. That should be not the conclusion or the hypothesis, right? So not the conclusion is not P, or the hypothesis, Q or R. And I believe that actually gets it done, right? So we just have nots and ors in this case. Yeah. Is that good, or did you want to look at the second part?
No, that's good.
Okay.
I don't know if I read on the rule wrong, but I wrote not P.
Yeah, I messed up.
Oh, you meant, oh, no, I should have thought. That's fine. I should have thought about it for a second. So it's not P or R? So, or R, yes. Or Q. That's what it should have been.
Yeah.
I apologize, I should have caught that. So now, let's redo it again. Okay, so this time, this is not hypothesis. Not hypothesis would be not Q or R. Or conclusion or P.
Yeah.
Is that better? Yeah, sorry about that. I should have noticed that. Thank you. Any other questions? Okay. I think that that's a good place to end for today. I could start a new section, but I think it's better if it's all together. So that's it for today. Thursday, we will do presentations. If we get done early with presentations, it's not usually the case, but if we do, I'll cover a little bit more stuff. Yeah.
Is 1.3 assigned?
It is, yeah. So this section that we just finished, 1.3, is assigned, and it will be due a week from today. So homework 1.3, just in case you want me to write it down right now. 1 through 11, 16, 17, and 18. Yeah, and 1.2, you can hand the whole thing into Cassandra before you go. Okay, have a great day. I will see, yeah, no problem. Have a good day, and I'll see you on Thursday. And remember, please, to email me your presentations before Thursday morning. Thanks.
On grading,
Yes.
so if there's one question that's wrong, and say there's more than 10 questions assigned, do you want me to take like 1 point or just find whatever the fraction is?
Yeah, just like, if there's a small error, just like take a little bit off.
Okay.
Not a whole point or anything, like, but you can do that over the whole assignment. If you're taking off like halves or fourths, whatever you feel is appropriate, probably for us for small mistakes. Then it's just like, let it add up over the whole set of problems.
And then is 1.3 the first assignment with proofs, or is that the next one? I haven't looked through with the.
There's no proofs on the one they're handing in today, I don't think, but there will be on the next one.
Okay, so then they should all turn in one sheet per page.
Yes.
Okay, awesome. Thank you.
Yeah.
I have a quick question
Sure.
about the presentation.
Yes.